Yes. So thank you, Pasquale, again for giving us this talk. Quick introduction. Pasquale got his PhD on the production of high-energy gamma rays and compact sources. His expertise is on cosmic ray acceleration. His PhD was from the University of L'Aquila. Since then, he's had a very illustrious career. He's been visiting professor, research associate at various institutes, at Fermilab, at Santa Barbara, University of Chicago, Kavli Institute, Cosmological Sciences. And currently he is at Gran Sasso Science Institute, where he's been there for a while. So his research expertise has been on particle acceleration in supernova remnants and star clusters, pulsar wind nebulae, galactic ultra-high energy cosmic rays, and also interesting areas of phenomenology, dark matter annihilation, as well as neutrino galactic gamma ray neutrino astrophysics. The title of today's talk is Escape of Cosmic Rays from Sources. It's a pretty broad topic, so we are looking forward to this. And I also wanted to say that today is the last talk of the series for the semester. As you know, we've been running these seminars as part of the Extreme Non-Thermal Universe CDY Initiative. We will resume again in the fall, so you can check out our website. But until then, we look forward to seeing you again in the fall after today's seminar. If you want to sign up directly with our mailing list, please send us your email and we will add you to the mailing list. So thank you very much, Pasquale, and please get started.
Yes, thank you for the invitation to close this cycle of seminars. I'm really proud of being the last one. I hope you enjoy it. So Rashmi was mentioning this is a broad topic, and it is indeed. It is also, if I may, perhaps it's a little bit of an unusual topic because most of the discussion about cosmic rays either focuses on the particle acceleration part or about the cosmic ray transport part, and for very good reasons, of course. But the question arises of when do you start talking about transport and when does the acceleration end? And there is this gray area of the transition from the accelerated particles to cosmic rays, which is all but clear. And in fact, the point that I want to discuss with you is that this phenomenon is in fact of very high relevance, not only as a theoretical problem, but also for the phenomenological implications that it has. So I want to start with a slide of why is escape from an accelerator important. I want to stress that here I'm trying to use the words cosmic rays and escape and sources as a, in a very general sense. So cosmic rays, I mean here, whatever particles you may be interested in, from electrons and positrons from a pulsar wind nebula to cosmic rays, cosmic ray protons from a supernova remnant, or ultra energy cosmic rays escaping the host galaxy. In all these situations, in fact, the phenomenon of escape plays a very important role. So let's see why. Well, first of all, one consideration is that the spectrum of the accelerated particles that you may calculate from first principles or from phenomenological considerations in the source is in general different from the spectrum of cosmic rays that escape the source and acts as a source term in the so-called transport equation. This is one first point that I want to make. The other consideration is that, at least in the galaxy, where we start from a situation in which the ISM is in roughly thermal pressure equilibrium between gas, magnetic fields, and cosmic rays, it is obvious, or somehow it seems obvious, that near a source, the energy density of the cosmic rays needs to be much larger than the pressure of the ISM, so that you may and should expect dynamical effects on the environment around the source. There is another point, of course, that not only the density of particles around the source is large, but the gradients of the particle densities are large. But the gradients in this business are basically gradients of charged particles, electrically charged particles, like protons, for instance, which means that in general you have strong currents near a source. Therefore, you may excite instabilities and phenomena that turn out to be interesting. From the theoretical point of view, you should keep in mind that escape is in the end what defines the boundary conditions for both an acceleration or a transport problem, something that we usually put by hand, right? When we solve the transport equation of cosmic rays in the galaxy, we usually adopt the so-called free escape boundary condition, which means that the particles escape whenever they reach some surface, right? And very similar situation is in the acceleration region. So I will limit myself to discussing three cases here, which is the case of supernova remnants, pulsar wind nebulae, and perhaps an entire galaxy like ours, or a source of ultra-energy cosmic rays. And these three instances, I hope that will clarify why the escape is an important phenomenon to keep in mind. So let's start from supernovae. Well, the first point I want to make is that, of course, escape is crucial for the particle acceleration process to work. What we learn in elementary courses is that particles may be accelerated in supernovae because of diffusive shock acceleration. And the idea is very simple, as you should know, as you might know, namely that particles crossing the surface of a Newtonian shock eventually gain at each cycle an energy delta U over E, which is proportional to the jump in velocity of the plasma across the shock surface. Now, the spectrum that you get from this process is absolutely independent of the details of the microphysics. For instance, the diffusion coefficient never enters the calculation of the spectrum. And that's the good news. The bad news is that without knowing the diffusion coefficient, you cannot estimate what's the maximum energy, because diffusion sets the time scale for the process to take place. Therefore, from the microphysics enters when you try to calculate how long does it take for a particle to be accelerated up to some energy. I want to stress that typically the acceleration time is written in terms of the residence time upstream and downstream of the shock, which sort of makes sense. But you understand that the crucial part for diffusive shock acceleration, at least in a supernova remnant, is this first term here, the diffusion coefficient upstream. If, in fact, the diffusion upstream of the shock is just the standard diffusion that we experience in the galaxy, it can be shown very easily that the maximum energy for typical parameters of a supernova is exceedingly uninteresting, in the sense that it's in the GeV range, therefore the acceleration really doesn't work. And the idea is that, in fact, the streaming of particles in the upstream region may be responsible for the excitation of either resonant or non-resonant, depending on the regime in which you are, instabilities, and these are responsible for magnetic field amplification. Now, very quickly, what are we talking about here? The standard resonant self-generation of alpha waves is something that was studied already in the 60s. The idea, I think, can be explained without going into too much details, thanks to an argument that Closford put forward. Namely, what the particles try to do when they diffuse is really to imagine a cannon that is shooting cosmic rays, and eventually the cosmic ray, the diffusion process leads to change in the pitch angle of the particles, which means that the momentum in the z direction gets lost. And that means that it has to go somewhere else. And the main thing in which it goes is, in fact, momentum of the waves that are present there. So in other words, even intuitively, it is clear that you may amplify the alpha waves that are already present in the environment. And in fact, the diffusion should stop whenever the waves and the particles move together. Therefore, the momentum change in the z direction can be simply written as the difference in momentum between the drift velocity and the alpha end velocity, or wave velocity, in a time which I call here tau 90, namely the time necessary for deflection by 90 degrees. And this has to go into, at the same rate, let's assume as the first instance, needs to go into waves. So the energy density of the waves is d squared over 8 pi. And if I introduce this gamma, which is the rate of gain and momentum of the waves, I can, by equating these two, estimate what this gamma is. And with a factor of 2, you basically get the right answer that the growth rate of this instability is proportional to the ratio of the density of cosmic rays to the density of gas of ions in the environment, and proportional to the difference in velocity between the drift speed and the alpha end velocity and the cyclotron frequency. Now, if you put the numbers in for a typical supernova shock, you would get growth rates which are extremely high or relatively high. So of the order of days or weeks for relatively low energy cosmic rays. So this is clearly a phenomenon that needs to be taken into account, that it has been taken into account in much literature on the topic. There is another process which is relatively recent, in fact. It has been studied, proposed, and discussed by Tony Bell in 2004 using an MHD approach, and later we tried to provide a kinetic approach to the same instability. The idea is simple. So if you imagine that this is a fraction of the surface of the shock that is moving into the ISM, it is carrying with it the protons, the positively charged particles that it's accelerating, and therefore it looks like a current propagating into the ISM. The plasma in the ISM doesn't like this net current occurring, therefore it develops a relative motion between protons and electrons, which lead to a return current. Now, you can see that this configuration of two currents may in fact be unstable. I say may because this condition needs to be realized, namely the energy density in the streaming particles needs to exceed the energy density in the pre-existing magnetic field. One peculiarity of this instability is that, contrary to the previous one, which occurs at the resonance scale. So in other words, you excite waves which have exactly the same wavelength as the alarm radius of the particles. In this case, this is not true. In general, you excite perturbations on much smaller scale. Now, you should understand that diffusion per se requires almost invariably that the particles interact resonantly with alpha waves. That's a situation in which most of the scattering takes place. Therefore, at first instance, you would say that this configuration does not lead to efficient scattering. However, what has been shown in a lot of numerical work, but also it can be understood in a more physical way, we'll come back to this later on, is that the J cross B force, where J is the current of cosmic rays in the streaming, eventually lead to the creation of loops. And when the loop size becomes comparable with the Raman radius of the particles, you again can scatter effectively off those perturbations. It can also be shown that, going back to the previous slide, not only this is a condition for the excitation of the instability, but it also sets the level of saturation. In other words, the instability stops growing when the energy density in the field is the same as the energy density in the streaming particles. So this is what is written here in terms of the cosmic ray acceleration efficiency at a shock moving with velocity vs. So you see that the magnetic field is roughly proportional to the cube of the velocity of the shock. So this is of course, these are of course ways in which the magnetic field can be increased, and therefore the diffusion coefficient can be reduced, thereby enhancing increasing the time of resonance of the particles in the upstream, and therefore increasing the maximum energy. Now, what's the point that I want to make? The point I want to make is that you need escape of the particles in this second scenario for the escape to be avoided. What I mean is the following. Imagine a sort of very toy model in which there is a first generation of particles that manages to cross the shock and go into the upstream, where there are no perturbations now, so that these particles here represent a real current of charged particles leaving the system. They are escaping in all respects, but by escaping, they produce perturbations. Therefore, the next generation of particles of the same energy eventually get scattered. Therefore, they go back to the shock and they return again upstream, but with a different energy. And the situation is repeated again. So you need escape so that the next generation of the particles with the same energy doesn't escape. This is also seen in simulations that Damiano and Anatoly have ran already 10 years ago or so, and there has been a lot of work after that in which you see these magnetic perturbations being excited very far away from shock itself. So there are particles that actually reach far upstream and create the conditions for the next ones to not do so, to be confined closer to the shock surface. So the first point I want to make, again, is that you do need some particles to escape so that the next generation is not allowed to escape as effectively. Now, there is another point to keep in mind, that, as I said in the beginning, the spectrum of the particles accelerated at the shock is different from the spectrum of the particles that eventually escape the supernova remnant. Now, concentrate in all this mess of curves, please concentrate on the orange thick line here. This is the total spectrum escaping a type 1a supernova, type 2, or what I call here a type 2 star, which is an object with the same property of a type 2 supernova, but now with energy, which is about 10 times larger as usual. Now, you can see that the flat line in this plot corresponds to P2 minus 4, which is the spectrum of particles accelerated at an ordinary Newtonian shock. And you see that in general, what escapes is all but a problem. It has bumps and dips, which correspond to the fact that that the spectrum of escaping particles is made mainly of two components. One component, which is the particles that are accelerated at the shock and eventually advected in the downstream and escaping at a much later time after adiabatic losses. And the second is the particles that can escape from the upstream. Those are the ones I was referring to earlier in this talk. And you see that depending on the situation, depending on the presence of a wind of the progenitor or not, the spectrum that escapes into the ISM is very different. And especially it's not a power law. So for instance, I am just speculating here. I'm not saying that this is the explanation, but a dip in the spectrum of cosmic rays at 10 to 4 GeV or so, at 10 TeV or so, is all but surprising in this business because of the overlap of these different components of escaping particles. Well, particles do escape. So let's go and discuss a little bit about the what we should expect, at least based on orders of magnitude estimates in the region around the source. And of course, you can do this in many different ways. Let's try to get some numbers right here. So you can imagine a supernova exploding in a complicated galactic magnetic field. I'm using here LC to indicate this typical coherence scale of the magnetic field in the galaxy, say of order tens of parsec or so, between 50 and 100 parsec or so. And you can estimate the density of cosmic rays escaping in one dimension along this the local magnetic field line. And you can compare it with the sea, the density of the sea of cosmic rays in the galaxy, which we know very well how to calculate, because if you know the rate R of supernovae and the spectrum contributed by each individual source, you know the size of the halo and diffusion coefficient. Notice that this H over D is exactly what is what can be measured through the boron over carbon ratio. Then you can easily calculate this one and compare it with this, and you easily see that the contribution from the individual source dominates for tens of thousands of years, at least in the low energy part, over the sea of cosmic rays. Therefore, for at least several thousand years, the pressure in the form of newly injected particles into the ISM is bound to dominate upon the typical density of cosmic rays and the pressure of cosmic rays in the surrounding medium. Yeah, so this is the main point I want to make. And the reason for making this point is that since it is so, one should expect that that region is affected by both local dynamical effects. By local dynamical effects, I mean action on the plasma. So evacuation motion, vorticity, heating, and stuff like that, and magnetic field modification, amplification, shears, and so on and so forth. Also notice that at least for as long as it lasts, the self-generation is a sort of positive feedback. If you produce perturbations, that reduces the diffusion coefficient. By reducing the diffusion coefficient, this increases the density even more, but reduces the gradients. So it is a complicated process, which most likely results in some sort of self-regulation. Now, this is an example of a calculation for parameters of a supernova remnant, relatively normal parameters of a supernova remnant, in the region around the supernova itself, in the presence of self-generation. So here only the standard resonant instability is taken into account. And what you can see is the following. Here, this gray line here is the diffusion time using just the galactic diffusion coefficient, so nothing weird is happening here. And you see this tens of thousands of years that we estimated earlier on in one of the previous slides. On the other hand, if you turn on self-generation, the typical, the production of waves due to the streaming of cosmic rays leads to production of additional perturbations, which reduce the diffusion coefficient and increase the propagation time. So the confinement time increases by at least an order of magnitude in typical conditions, although it is a strong function of the environment. So it is different whether you assume that the medium is very low density but highly ionized, or large density and mostly neutral. The main reason for this is in the dampings of these waves. For neutral gas or quasi-neutral gas, you have, of course, to propagate these alpine waves in a medium which is mostly neutral, which means that basically protons act as an inertia on the propagation of the wave, and therefore the wave gets damped very easily. On the other hand, notice that if you reduce the density of the gas, ion-neutral damping almost disappears, or it's much lower, but the propagation time remains relatively long. In this situation, nonlinear Landau damping is the main process of reduction of the waves themselves. So what changes in these two cases is the amount of grammage that the particles accumulate. And this is a very important point, especially for the phenomenology that I will try to discuss later on. So it is obvious that near a supernova remnant, at least, the effects that the propagation of the particles have may be very important, even for their own, for the grammage accumulated by the same particles that are trying to leave the source. One may ask, what if the overall density in the region around the supernova is relatively low? Because, for instance, there is a bubble of ionized gas around, but a molecular cloud happens to be there. Well, this is a delicate point, and it has been studied by many, many people, and one has to be extremely careful in selecting the type of sources to study in this way, because the reason I'm saying this is because you can easily get fooled by what data are telling you. For instance, when selecting sources of this type, you want to make sure that the shock of the supernova itself is not touching any molecular cloud. The reason for that is that the molecular cloud is mainly neutral, and therefore, and that it has a high density. Therefore, the shock velocity drops very quickly when it hits the supernova, therefore, when it hits the cloud, therefore making the process of acceleration much less efficient. Not only that, but only the ionized gas takes part in the acceleration process, and that means that a smaller number of cosmic rays can actually contribute, can actually enter the acceleration box. Not only that, but again, the large density of neutrals implies strong damping of the waves and again, weak acceleration. So you want to make sure that you want to study, in order to investigate the escape, you want to study supernovae, which are in a region where molecular clouds are present, but not in direct contact with them. So of the several cases that we have analyzed, perhaps the only one that seemed to fall roughly in the right ballpark is HB9, which is an old kind of boring supernova remnant. Not particularly exciting, but the gamma ray emission shows this low energy turnover, which is one of the signatures that people look for. The reason is obvious, and you can understand easily by using phenomenological models. Phenomenological, I mean, you fix the diffusion coefficient and you calculate what needs to be in order to explain the data. Why do you expect a low energy turnover? Well, because it might be that low energy particles didn't have enough time to reach the molecular cloud. And by requiring that, you can put a limit on the suppression of the diffusion coefficient. And the suppression is this factor K that I indicated here in the legend. And you can see that most of the curves require a suppression of the order of 50 to a few hundred. So you would say, well, that's great. At least phenomenologically speaking, I can argue that this is a case in which the diffusion coefficient is in fact suppressed. You can try to do a little bit better by assuming some self-generated models. So introduce the calculation in the calculation, the excitation of the streaming instability. And again, you seem to get a good fit to the observations by requiring that that substantial self-generation is occurring. But, well, unfortunately, it is another ambiguous case. For the reason that this supernova is relatively old, the maximum energy, you can estimate it, but not very solidly. And if you estimate, you get numbers in the range of a few TeV, in which case all the considerations I gave you are fine. But if the maximum energy at the source were in the range of 100 GeV, then it could be simply that the particles of 100 GeV are being accelerated right now. And therefore, they didn't have time to reach there, not because the diffusion coefficient is suppressed, but simply because they didn't have enough time to be produced. So again, you can repeat the same example as before. And again, the situation is ambiguous. If the maximum energy is of the order of 100 GeV, then again, you have a situation in which the diffusion coefficient can be exactly the same as in the rest of the galaxy and get a good fit to the data. So I would conclude that at present, there is no absolutely solid case in which we see suppression of the diffusion coefficient, which doesn't mean it's not there. It just means that it's really difficult to look for this phenomenon in a clear way, in a clean way. There are usually other factors that may provide another explanation of the same set of data. However, the phenomenon per se has a very strong motivation. So to some extent, it has to be there. And so in a period in which the grammage accumulated by cosmic rays in the galaxy is measured at a few percent level, you cannot afford to leave an effect like this unexplored. So let's see what happens to the grammage accumulated by cosmic rays while they're trying to leave the source. So this is this region of escape that I'm referring to. I considered here two extreme cases, if you wish. One in which the density is very small, but everything is ionized, and one in which the density is large, but there is an equal number of ions and neutrals, so the level of ion neutral damping is relatively strong. So you see that the grammage accumulated in the presence of a molecular cloud in that region with a column with a density of 800 particles per cc inside the cloud, well, is very prominent. You see that in the optimistic case in which the density is low, the density outside is low, then you accumulate a lot of time, and the accumulated grammage can easily exceed the grammage in the galaxy. So clearly this is an extreme situation, but just to illustrate the importance of this class of phenomena. In the case in which you have neutral gas as well, you see that actually there is this strange behavior in which the grammage increases with energy above 100 GeV. This is the effect of the fact that ion neutral damping is especially important for low energy particles. Therefore, there is no appreciable self-generation down here. And then you have appreciable amplification of the magnetic field for particles with larger energy. So again, if you remember that the grammage in the galaxy accumulated for 10 GeVs of the order of 10 grams per square centimeter, you understand very easily that this phenomenon, again, cannot be easily ruled out, cannot be easily neglected. You have to provide some justification of why it should be neglected. A closer look at the situation, which is a little bit different from the one we analyzed before, namely that of a young supernova event. By young, I mean that the shock didn't have time to move too far away from the supernova, from the explosion location. That means that most of the particles are injected in a narrow tube, which increases the density of particles there. And again, in this situation, you can actually check that for particles with energy TeV or so, the path length in the galactic magnetic field is of the order of 30 parsec, which is comparable with the coherent scale of the field. And the reason why is that important, why that is important is that this is effectively a current of particles that are ballistically or almost ballistically moving away from this object. So you again you can estimate what is the energy density in the streaming particles, and for a sufficiently young supernova remnant, you get that it exceeds the magnetic field energy density in the ISM. So we asked ourselves, can we understand a little better what happens in this situation? Well, what we did is to use a hybrid tech simulation to study this. The region here with a supernova is the place where we inject the particles that are going to move in the positive direction. So they're moving this way in a basically ballistic manner, although we are injecting them with a semi-isotropic distribution of pitch angles. And you see that in the beginning, they in fact go roughly ballistically in the Z direction, but almost immediately, the energy density in those particles is sufficiently large to evacuate a region around the source, and they also start producing so-called Bell modes, or these non-resonant perturbations. If you keep going, you will see a couple of things going on. First of all, that because of the amplified magnetic field, the density of particles is larger, becomes larger because, again, as I said earlier, the more magnetic field you produce, the lower is the diffusion coefficient, the larger is the density. So particles accumulate even more. And now, since there is not enough pressure on the sides here, the bubble tries to expand laterally. And so you see that there is an evacuation of the region where the particles were before, and eventually you have the expansion in the outside, in the perpendicular direction. If you still go forward, you see that this phenomenon continues, and the bubble becomes, well, not spherical, but almost. And the region around is, inside, sorry, is evacuated. Now, this is 2D simulations. And of course, as usual, with all these kind of simulations, you have to use parameters which are not exactly physical. For instance, the outflow speed is only C/20. But still, the physics that one would expect naively is, or seems to be, confirmed by these simulations. We tried, well, this is just to show that, in fact, what is happening is that particles start diffusing. The blue distribution here is the distribution of momenta in the x direction in the beginning, and you see that they are all positive because the particles are streaming all in the positive x direction. But at a later time, the particles have already started diffusing and they're populating the region in the on the other side. So the diffusion process has by then become effective. We tried just to make sure that there was no artifact of the reduced dimensionality. We repeated this calculation in 3D. Of course, the dynamical range is smaller, but it seems like the phenomenon, now this is seen face on, so the tube is in front of you now. The current is coming towards you, and you see the bubble of cosmic rays which become denser, and the bubble excavated in the plasma barrier. Now, so as the only main difference I would say that you see is that there is much more mixing. So there is gas from the outside that penetrates the region, which was evacuated completely in the 2D situation. So this basically to make, let me go back here, in a, I think, rather solid way, solid manner, the following point. Cosmic rays in the region around the source can easily produce both self-generational perturbations, which reduce their own diffusivity, and by doing so, increase their pressure and therefore enhance dynamical effects on the region around the source. And to my knowledge, there isn't much investigation, probably none, of these phenomena so far. Now, I want to switch gear and discuss another situation, that of escape from a pulsar with nebula. The main reason for doing so is, well, two reasons. One is that we observe a few cases of the so-called TeV halos, which are regions bright in the range of 10 to 100 TeV or so, around a couple of supernova, couple of pulsar wind nebula, in which the morphology of the gamma ray emission suggests that the diffusivity is reduced by at least 2 to 3 orders of magnitude. The second is the filaments of X-ray radiation that are produced by Bow-Shock nebula, a few of them. We have 3 cases right now, in which, again, you can estimate the strength of the diffusion, the strength of the magnetic field from synchrotron losses, and you get magnetic fields in the range of about 50 to 100 microgauss, substantially larger than the magnetic field in the ISM. Now, whether these two phenomena have the same origin or a similar origin, or whether we can learn from one about the other, is all but established. But I wanted to discuss this because it is similar to some extent to what we discussed earlier, but also different. Different mainly because these are electrons and positrons. Now, electrons and positrons, if they actually escape from the Bow-Shock nebula in a co-spatial way, would lead to a zero current. Therefore, many of the considerations I discussed earlier are probably not applicable. On the other hand, it is known, but at least from simulations, for instance, Salmi and Bucciantini in 2019, that at least close to the maximum potential drop of the pulsar, it is possible that electrons and positrons escape in a non-conspatial way. In other words, positrons go one way and the electrons go the other way, in which case, of course, the net current is non-zero. So what we did is to try to consider this situation. You have a pulsar wind nebula, which is moving through the interstellar medium with a velocity of the pulsar going this way. And you see, for instance, in the case of J2030, or in the case of the guitar as well, that there are these very long parsec-size filaments and very narrow filaments of X-ray radiation. And again, if you interpret the thickness of these filaments as resulting from synchrotron emission, then you would infer that the magnetic field in there is of the order of tens of microgauss or so. So what we did is the following. Let's assume that because of some reason, for instance, a reconnection point or something, a beam of electrons or positrons actually manages to escape the pulsar wind nebula. And to escape at the Lorentz factor, which is a little bit below, we will have to establish how low, lower than the maximum potential drop of the pulsar, which, as you know, can be expressed as only a function of the E dot, the spin down luminosity of the pulsar itself. You can easily estimate the current of the electrons or positrons that are escaping through this point, assuming that they are all focused in a region A of surface A. And again, A can be calculated a posteriori in order to fit the parameters of the problem. So you can easily see what follows. So you can actually calculate the growth rate of the instability that is excited by this beam of particles. Remember now that the energy density is not that large, so it's difficult for the energy density per se. If they were emitted isotropically by the pulsar, it would be difficult to exceed the energy density in the magnetic field of the galaxy. On the other hand, if these particles were strongly focused in a given direction, then you can calculate how large should this collimation be, the sin alpha be, in order to actually produce a thin enough tube of particles where the density is large. And you can also estimate the magnetic field at which you saturate at the end of this instability. Now, please keep in mind what is the dynamics of this phenomenon. The instability I'm talking about is the non-resonant instability. So you have this current that is piercing the ISM. The particles leave and go very far away from the pulsar nebula for a time which is of the order of a few growth times. And only then the instability is the magnetic field has grown enough so that the particles start diffusing. They isotropize, and that's the emission of the X-rays that you actually see. So by doing this game, by playing this game, you can actually calculate at the same time the length of the filament that you expect and the thickness of the filament that you expect. And for instance, for the case of, let me go here, for the case of the Guitar Nebula, for the parameters of the Guitar Nebula, what you can see is that in order to get a filament of 0.6 parsec and a thickness of 0.08 parsec, what you need is an efficiency of the particles of 7 times 10 to minus 3 of the E dot, and then escape Lorentz factor, which is about 1 order of magnitude lower than the maximum potential drop. The magnetic field that you calculate in this way is of the order of 70 microgauss. So it seems like things are fitting together in a relatively nice way. So here again, the situation of the escape is rather different from that of a supernova because we don't have protons, we have electrons and positrons, and you have to speculate that they escape in a charge-separated manner. Now, it is also different because, again, if you, we observe, as I said earlier, two instances of reduced diffusivity here. One is these filaments, which translate into an amplified value of the magnetic field. The other one is the TV halos. At present, I cannot say whether the two phenomena have the same origin, but certainly the phenomenology that we observe is very similar. In one case, it's a filament. In the other case, it's a larger region in the form of a bubble of about 20, 30 parsec or so, in which the diffusivity is about 2 orders of magnitude, 3 orders of magnitude smaller than the typical ISM. Again, the suspicion that this may reflect the action of some locally escaped particles is strong, and I think it is a direction to be explored. Finally, I want to consider, at this point, let's go to larger scale. Let's consider the whole galaxy. And I want to start from a really simple TUI model exercise, which illustrates the importance of the phenomenon. So let me remind you what people do when they study transport of cosmic rays in the galaxy. Of course, you can do it with an arbitrary level of complication. You can use sophisticated codes, but the essential physics is the same. And even the mathematics is very similar. What we do invariantly, depending on whether you do it analytically or numerically, what you do is always the same thing. You assume that the sources and the gas are in a relatively narrow region, which we call the disk. And then there is a free escape boundary condition. That's the boundary condition that you need to impose by hand to solve the equations. You assume that the source term is a delta function in Z or a narrow distribution in Z, and you solve the transport equation, which at the zero order, the simplest model is just a diffusion equation. And this is the free escape boundary condition. This can be solved by a student in 30 seconds. And it shows that the distribution in space is linear in Z. And not only that, but it's you can calculate from here the derivative of the distribution in Z, which, as you know, is the flux of the particles. And this flux remains constant. Therefore, you can easily integrate that equation and see that the distribution that you measure in the disk of the galaxy is whatever you inject multiplied by the diffusion time, the confinement time, as we call it, right? So far, so good. Also remember, notice here that the all result depends only on the ratio H over D, which is exactly what you measure from Born over carbon or secondary over primary ratios. Now, where is the interesting thing? The interesting thing is that the flux is constant. Therefore, if you calculate the flux of particles escaping the galaxy, it is exactly as the flux, equal to the flux that you injected. No surprise there, but it is sometimes surprising that an observer sitting right outside our galaxy would not see the same thing that you are seeing in the disk of the galaxy, but the same thing that has been injected. What are the implications of this? Well, let me go back to this later if I have time. What are the implications of this? Well, you have at this point these particles, and you know exactly what the current that they transport, because it's the same current that you are injecting through supernovae or star clusters or whatever you wish to speculate upon. If the magnetic field in the intergalactic medium surrounding our galaxy is lower than about 10⁻⁸ Gauss, then again, you find yourself in a situation in which you excite a non-streaming instability, and growth time is only of the order of a couple of years. Therefore, it's a very strong phenomenon. What are the implications of this? Well, it's very strong because, well, first of all, you can easily calculate what's the saturation magnetic field, and exactly as in the previous case that I discussed in the beginning of this talk, the saturation field is coincident with the threshold for the excitation of the instability. So the net result is that the streaming of the cosmic rays from our galaxy should produce a magnetic field around the galaxy of the order of 10⁻⁸ Gauss or so. But not only that, but if you calculate how what is the diffusion coefficient associated with this, it's so small that in fact, not only particles are not free streaming, but they're actually stuck once they move outside the galaxy. And their pressure gradient becomes so large that in fact they start moving things around, and they should leave the galaxy, go away from the galaxy roughly at the alpha n speed in the local medium, which is of the order of a few hundred kilometers per second. So as you see, if you start from the assumption that they are free escaping, you get to the conclusion that they can't. So you understand that, again, the escape of particles even from the galaxy, in fact, is changing the boundary condition or is setting the boundary condition of your transport problem. And of course, the all problem should be solved together. There are a few people that have tried to do so, including us, but it's a difficult problem that at some point needs to be addressed properly. So what are there some implications? Well, yes, of course, you know, the obvious implication is that if it is true that these cosmic rays get accumulated in the region around the galaxy at some point, at some distance away, if the density of gas around there corresponds to an over density compared with the omega baryon rho critical of the order of 100 or so, as you would expect in a visualized halo of dark matter, then you know the flux of gamma rays and neutrinos is not that different from what we observe as a diffuse background. I'm not claiming that this is the explanation. I'm just saying that, again, the neglecting these effects is leads to all but trivial implications. So we should be careful when we identify diffuse fluxes of gamma rays and neutrinos as really diffuse or rather due to metagalactic phenomena. And there are several people that have speculated about this, including Andrew and Felix some time ago. So the same phenomenon, of course, that we have discussed in the case of our galaxy, you can repeat the same considerations for sources of ultra-energy cosmic rays, whatever they are. So you can again speculate that cosmic rays escaping a source at this point will be probably an active galactic nucleus or something like that. Well, they try to move in some direction, but provided the magnetic field around is lower than about 8 nanogauss or so, they will be actually producing exactly that magnetic field. Not only that, but the time required for these particles to leave the region around the source at sufficiently low energy can be longer than the age of the universe. Now, you understand that this implies that the spectrum, again, of cosmic rays leaving the source has little to do with the spectrum at the accelerator, because in this case, the spectrum that you expect to be liberated into the ISM, into the intergalactic medium at this point, will have a low energy cutoff. And some recent work I've been doing with Marta D'Angelo and Elena Amato, but more recently with Alessandro Cermenati, a student here, is that, in fact, a cutoff at low energy arises naturally in the 10 to 17 to 10 to 18 electron volts range. And not only that, but basically each source of ultra energy cosmic rays should have a region around which has a magnetic field of the order of a few nanogauss. This value here scales as the square root of the luminosity of the source. So it has some dependence, of course, but it's not terribly strong dependence on the luminosity of the source. We are trying to understand what is the effect of the change in the luminosity of the source on the strength of this magnetic field, on the implications for the Faraday rotation, and of course for the transport of ultra energy cosmic rays. I think it's time for me to conclude. Why should you want to understand ESCAPE a little bit better? Well, let me summarize what I said. Well, first of all, the obvious thing that ESCAPE is really a sort of a summary of the microphysics of plasma particle interactions that represents sort of a missing link between the physics of the accelerator and the physics of transport on larger scales. It sets the boundary condition for either problem of particle acceleration and cosmic ray transport. In the case of supernovae, as I showed to you, not only these phenomena are important for the maximum energy of the accelerated particles, but also to set the time that particles actually spend around the source. And this can contribute to the grammage that the particles accumulate in that region around the source. In the case of the pulsar wind nebula, you see at least two different phenomenologies, one in the TV halos, one in the X-ray filaments, in which you see reduced diffusivity, substantial reduced diffusivity, and relatively large, at least in the case of the filaments, relatively large magnetic fields. It's not clear yet, and I don't want to speculate too much about the fact that the two phenomena might somehow be related. In the case of escape of cosmic rays from the Milky Way or from any galaxy, including a source of ultra energy cosmic rays, the implications are substantial. Namely, first of all, diffuse neutrinos and a magnetized region around every source, but perhaps even the appearance for strange, let's call them odd spectra observed by Auger. As you might know, the Auger spectra with mixed composition, mass composition, require unusually hard spectra that look pretty much like suppressions of the flux of particles below 1 eV or so. A few years ago, I would have told you that this is pretty much speculation and that's it. It's not worth probably investigating too much. But now the situation has changed. Now we can actually measure the grammage with observation of boron over carbon and similar phenomenologies at the percent level. So even effects which are important at a few percent level will sooner or later show up. Not only that, perhaps they are showing up because there are hints, and maybe they are just hints, maybe they will disappear, I don't know, but certainly there are odd things popping out. For instance, diffuse gamma ray and neutrino fluxes from the Milky Way that appear to be substantially larger or with a harder spectrum at very high energy. Possible hardening of the B over C at energy per nucleon of TeV or so. It is worth recalling that some of these anomalies, of the anomalies in cosmic ray, for instance, the positron axis, have stimulated in the last 10 years or so a lot of speculations about alternative theories of transport, which imply the accumulation of grammage somewhere else, not in the galaxy. Now, these models have a lot of problems, especially the related to the decay of unstable isotopes, but still, it adds to a scenario, to a situation in which there are lots of different observables that suggest, at least, hints to the possibility that there is damage accumulated in addition to the one on transport of cosmic rays. And finally, I want to point out that finally, for the first time, we have good eyes, experimental eyes, telescopes that look at large diffuse sources like Ock and Lasso. So it is first time that we have a chance to actually look at the regions of escape of cosmic rays from the sources. And I would stop here and perhaps leave time for questions.
Thank you. Thank you, Pasquale. That was really excellent. Thanks for the summary. I'm going to let Felix, are you available to run the Q&A?
Yes, Rashmi, I'm here.
Okay, but I just want to thank Pasquale again, and
thank you.
Please continue.
Thanks, Rashmi. Hi, Felix.
Hi, Pasquale. Okay, let's start the first discussion and then, no, question, sorry. And then we could have afterwards some discussion. Questions?
There is Susumo with a raised hand and Jojun.
Yeah. Could I go ahead?
Hi,
yes,
Susumo.
Sumo, you go ahead.
Okay. Yeah, hi, Pasquale. Yeah, thanks for this really stimulating talk. So about the effects you discussed in relation to the escape from the galaxy, I'm trying to understand the relation with these scenarios of cosmic ray-driven winds, including your work with Sararekia, where I believe what is usually discussed is the resonant instability and heating of the gas due to generation and dissipation of the alpha N waves. So should I consider these as two alternative possibilities, or could it be that maybe the winds are occurring in the inner part of the galaxy and what you discussed maybe more in the outer parts or in the halo? Or
yeah, so the winds would actually happen. The winds would actually happen even in this very simple, even naive toy model that I have illustrated. The idea there is that since you have the solution that looks like this, right? So you have the solution in space looks like a linear function of z, where z is the coordinate here. Therefore, the gradient in the pressure of cosmic rays is proportional to F over H, right? That's the gradient of the pressure. If the pressure, if this pressure in the pressure gradient, is larger than the gravitational force, which is due this time to dark matter. So imagine that all of this is surrounded by halo dark matter. So the dark matter force is directed towards the center of the galaxy at this point. And you have two forces, one the gradient of the pressure of cosmic rays that points upward, and one is the force of gravity that points down. So you would excite a wind, you would launch a wind provided the force due to the pressure gradient is larger than the gravitational force. You may have a wind, you may have a fountain, for instance, a gas that goes from one side and falling on the other. My point instead is a bit different. So even if you take this zero-order model and you assume that the particles far away from the galaxy, so where gravity perhaps is less important, even in that simple situation, if you assume that cosmic rays are actually streaming away from the galaxy, you know exactly what that current is. There is no uncertainty in that because, at least if you neglect energy losses, which is a good approximation for protons at least, then you know exactly what is this current. The current is exactly the same as you injected. And at that point, you can simply check whether the non-resonant streaming instability, which cannot be excited inside the galaxy because the magnetic field is too large, if there is any room for that instability to grow. And you find that provided the field is larger than 10⁻⁸ Gauss or so, you do manage to excite the instability. Now, Perhaps to complete the answer to your question, I should add this slide, which I adding, but I skipped because I had no time. And in fact, I wrote in passing. So there have been a couple of attempts to solve the problem of cosmic ray transport in a galaxy, but simply using self-generated turbulence. So the halo there is not fixed. So there is no free escape boundary condition at some finite surface, okay? In these kind of approaches, the halo is sort of self-generated, self-produced. So it becomes larger or smaller depending on the injection of cosmic rays from the disk of the galaxy. And again, the idea, basically speaking, is that at some distance from the galaxy, the self-generation becomes so effectively that particles get stuck there, and therefore at that point they just move effectively with the offense speed. And the place where this happens depends on energy, which is the reason why the spectrum at the Earth is different than the spectrum at the sources. So to answer your question, they are related, and it is definitely true that all this stuff is based on resonance dimming instability. While the thing that I'm pointing out is that independent of what happens inside the galaxy, if at some point these particles leave into the IGM, you know exactly what the current they carry is. And at that point in the IGM, they should be exciting these instabilities. So naively speaking, I would suggest that perhaps every source of cosmic rays should have a sort of a halo around where cosmic rays are not completely gone, even on cosmological timescales.
Yeah, okay, thanks. I think I said better. Yep.
We have another question. Jun Yong Wu, please.
Yes. Thank you, Pasquale. It's a really interesting talk. I have two questions about the molecular cloud and the supernova remnant stuff. I believe it's on page 14. I have actually two questions. Yes. So one is, you mentioned that in the second point, only ionized gas can take part, and the molecular cloud is neutral. So it's there are low number of particles to become cosmic rays. But then those neutral particles would be ionized if there are a lot of cosmic rays in the vicinity. And also high energy cosmic rays would initiate some inelastic scatterings to produce secondaries, which can also be cosmic ray seed, right? So I'm wondering how efficient that process would be. Would that, add a chance to have more cosmic rays?
Yes, no, you are absolutely right that there are a lot of nonlinear phenomena taking place. One is, as you suggest, that if there are lots of cosmic rays at low energy, they can excite and they can induce ionization and increase the level of ionization. Still, the number of neutrals is still dominant. So you increase the level of ionization, but the number density of ions is still relatively small. So when I wrote this slide, what I had in mind is the criteria that you need to fulfill so that you are reasonably sure that you look at the molecular cloud as a signature of the escape rather than the interaction of the supernova with the molecular cloud. The latter, the molecular cloud interaction with the supernova, has been studied by many people, and of course is dense with a lot of information about all the phenomena you mentioned. For instance, you can produce secondaries. The secondaries are reaccelerated, and this is both a source of electrons and positrons and secondary nuclei, and so on and so forth. So definitely that is the case, but at relatively low energy, because in that environment it's really difficult to accelerate to very high energies. And I wanted to sort of outline what are the essential conditions that I would require so that I'm reasonably sure that what I'm looking at by looking at the molecular cloud is the escape rather than the interaction with the cloud.
I see. I have another related question. So as you said, there are some studies on the molecular cloud interacting with the shock, and actually the density is so high that it sort of initiated the shock in the opposite direction. And I'm wondering, in that case, there would be a sea of cosmic rays already, and that might be another seed of the acceleration, and that process could be effective. So I'm wondering, do you have any ideas on how effective that process would be, if it's feasible physically?
So what you're referring to is it's some sort of reverse shock, right? So it's something that develops even in the ISM. When you hit the ISM, there are two shocks, one forward and one is backward. The problem with the reverse shock is always in normal conditions, not in molecular clouds, but it's always that the reverse shock is actually propagating in the ejecta, and there is very little magnetic field unless you self-produce it there too. So in principle, it is possible for interesting phenomenology to take place there too, but you have to take into account that the self-generation is already poorly understood at the strong forward shock. Imagine in the reverse shock. So it's just much harder to investigate. I'm not sure I've seen a treatment of this process of the reverse shock when you hit the molecular cloud, honestly. But it's an interesting question. So yes, it is worth looking into that. Again, from the point of view of the interaction of the shock with the molecular cloud, not in terms of the escape investigation of the escape clouds. Yeah.
Thank you.
Thank you.
Okay, Ruyo.
Okay. Thank you, Pasquale. My question is about this cosmically driven cavity. So you mentioned that after cosmic ray, I mean, due to the instability of cosmic ray, they will push away the plasma around the source and creating a cavity. So yeah, my question is that why such kind of low density cavity are observed sometimes in the ICM, but usually I think it's ascribed to like the powerful wind of the progenitor or the blast wave of the supernova itself. Then how to distinguish among the scenarios?
You are absolutely right. So those are observed, and they are known to be the result of the evacuation produced by the stellar winds of the progenitor. So I think that the answer to your question is that this should happen even outside of that bubble. So once the cosmic rays escape even that bubble, eventually they will find themselves in the conditions of evacuating the region around at larger distance. But you have to take into account that this phenomenon occurs only if the current density is large enough. So that's why I specified that this applies to a young supernova remnant. So you need something like a young supernova remnant, perhaps the supernova 1A. In the case of 1A, you don't expect those bubbles produced by the wind of the progenitor. So perhaps that's a cleaner way to look at. We didn't look at it from the point of view of the phenomenology that derives, but rather from the point of view of establishing that there are pieces of physics which are related to the escape of cosmic rays in principle that are important for the dynamics around the source.
Okay, thanks. Then one more related question. So I see you mentioned that the size of this bubble can reach like 50 to 100 parseconds. So how long would it take to reach such a large radius?
That's an excellent question, in fact. Because as you understand, in these kind of simulations, you can cover only a relatively narrow range of times, right? Yeah. And the expansion of this thing happens in the simulations at a velocity which is a few times the Alpine speed. A few times Alpine speed means in the ISM order, I don't know, 10 to 7 centimeter per second, something like that. So it will take a while before the expansion of before the expansion is completed. So the number, which I wrote somewhere here, right? You read it somewhere. I don't remember when I wrote it.
I think
Well, yeah, but you're right that it expands to about 50 parsec, and the way I calculated that here, the way I calculated that is by requiring that the energy put inside that bubble, if it stays in there, eventually expanding adiabatically just because of adiabatic expansion. So the pressure inside is much larger than the pressure outside. Therefore, the bubble expands and eventually reaches pressure balance in about 50 parsec or so. But it may take a long time before that happens.
Okay.
The process,
Yeah,
again, has not been studied by anybody.
I see. But that's very interesting because, but on the other hand, I think if it needs some time, then such kind of cosmically driven low density cavity should be. I mean, we should search for this kind of cavity maybe around like old supernova remnant or middle age supernova remnant.
Yes, I fully agree. I fully agree. In fact, one of the reasons why I didn't show it here, but one of the things we checked here is what happens to the product of the density of cosmic rays multiplied by the density of gas, because that in the end is a proxy for the gamma ray emission that you can see from the bubble, right? So I fully agree that it would be worth looking for that. But I would add perhaps a little bit more to this. For instance, in connection with the TV halo, it is often said that the TV halo is a symptom of a suppressed diffusivity by a couple of orders of magnitude. That's the current, trend of thought about this phenomenon. And there are a few possibilities, right? Either the diffusion coefficient is small everywhere, but that is a very dangerous thing to do because it affects easily other things like B over C and so on. Or it could be the result of the escaping particles. But escaping from where? It could be the positrons themselves, as I explained, but it could be the protons that have left the supernova remnant that eventually originated the pulsar, right? So the pulsar is sitting in a region, and it could be that that region has already been affected by the protons escaping the parent supernova remnant. So the answer to whether this is realistic or not depends on one aspect, which is unfortunately very poorly understood, the damping of the perturbations. What happened to those perturbations after the piston, after the current has disappeared? Is it possible that they persist for a sufficiently long time or not? And this is, again, a very difficult problem to solve.
Yeah, okay. Yeah, I agree. Thank you very much.
You're welcome.
Okay, some more questions. And maybe someone wants to make some comments or start some
Paolo
discussion.
has raised hand.
Yeah,
great talk. Yeah, I was curious for the filament, for the thickness, is that the expansion you're talking about here? Because you built up a huge field inside the filament for the escape from the pulsar wind nebula going out 70 microgauss. The overpressure will blow everything up kind of in your simulation. Is that taken into account, or?
Are we talking about this one now or the pulsar wind nebula case? This is for
the pulsar
supernovae.
wind nebula point escape filament.
Yeah.
But you've built up a very strong field, so why don't you get plasma evacuation in that case, or do you?
Most likely you do, but there you don't see the gas, right? You see the synchrotron emission.
Yeah. Yep.
So,
but will it blow
yeah.
itself apart and have a finite lifetime then?
Well, not on the time scale that we're talking about, right? So this is time scales for losses are relatively small, very short. So in fact, stuff that happens 30 years ago affects what we're seeing today. So not on these time scales, no.
Yep.
On much longer time scales, perhaps, which is the reason why I was speculating that I cannot exclude that these filaments might be the initial seeds of the TV halo, but it's all, a fuzzy idea in my head right now.
Okay, perhaps one other question. I was wondering, in some treatments of cosmic ray diffusion and confinement, people put in anisotropies, and when you're free streaming, there could be a strong ballistic motion, strong anisotropy, so your waves are going to be anisotropic. Is that taken into account? I've seen people assume everything is magically isotropic immediately, but Is there some regime we have to worry about anisotropy?
No, in fact,
Due
this
to-
is this is in fact the opposite limit. This is in extremely anisotropic here. Here, I only took into account parallel diffusion. There is no perpendicular diffusion at all. So the particles are only going back and forth around across the shock, across the filament. So
Okay.
the anisotropy you're talking about would reflect into the perpendicular part.
Right.
Now, eventually it will kick in again. And you can see it in the simulations that I showed before that, at some point the filament gets broader and the particles are moving also perpendicular, not only because of diffusion, of course, but also because of the plasma moving around, right? So it's more like advection rather than diffusion. I think that eventually it will kick in once the delta B over B becomes sufficiently large. We just don't know how to keep it.
Because I was thinking of some TV halo papers where they just assume everything is isotropic. If you actually, and that may be true, I guess, at large distance, but there's some intermediate scale where that may not be true, and that may change the intensity profile, possibly.
Well, I think the video got stuck, right?
Yep.
Okay, use the other camera. So I think you're right, but in the case of the TV halo, is a little bit less dangerous, right? Because the diffusion coefficient is suppressed by about 3 orders of magnitude in strength, just by from the morphology. Therefore, the time scale for 90-degree deflection is so small that it's really hard to imagine that over 20 parsec, the diffusion coefficient remains anisotropic. If the field were, in a given direction and remained in that direction, so delta B over B is small, then I would agree with you. But over such distances, I think it is hard to imagine. In fact, there are a couple of groups that have speculated that perhaps we are not seeing a reduction in the diffusion coefficient, but we are seeing perpendicular diffusion in case of the filament looking right into your eyes, right? So in that case, the size of the halo would correspond to perpendicular diffusion alone, which per se is much smaller. I think that this possibility, although it is worth being discussed, but will reflect one-to-one in the probability of having TV halos. So for now, we only have, 2, 3, something like that. So once we have a larger number of objects that we are confident they are TV halos, I think one can start doing some statistics and see what is the probability that if the field is oriented at random, you see that certain number of TV halos. You see what I mean?
Yep. Good point. Yeah. Thanks a lot. Yeah, that's good.
So I don't see any hands anymore. So then let's thank Pasquale again for the very insightful talk. And just a very short announcement. So this is a last talk of this semester. We'll start again sometime in September or most likely in October. We still should decide the topic. We'd like to have some more topicals, just at least to make several talks on the same topic. So please send your suggestions. I should admit that at this moment, we don't have a very clear view what we'd like to have next semester, but let's say until end of the year. So it's just for a couple of months, 3 months. And please don't hesitate to send all your suggestions, even they don't, much directly to the topics we have been discussed over the last 2 years, but we are quite open to also have talks which in a bit not in the mainstream, I mean in our seminars. So that could be even more interesting. So that is another thing. I think Reshmi already indicated that a few times. So now CDY CDY seminars will no, CDI activity will be not limited by seminars. We already had a workshop. We plan to have workshops, schools. So we had one workshop in New York last year on blazars. Will be another workshop on gamma ray loud binaries in October in Dublin. And we will have a school on gamma ray astronomy, basic school about detection methods, basic information about gamma ray astronomy in Heidelberg. It's called CDY Max Planck for Nuclear Physics CDY School. And we plan to have at least 2 workshops in 2025 and 1 school, summer school, also 2025. By the way, I was talking to yesterday, I'm attending a meeting with Carmelo, and he said that, I think Pasquale would confirm that the GSSI was going to organize another school basically on cosmic rays. So my first reaction was, unfortunately, I didn't discuss that with Reshmi and Paolo, but at least we'll discuss that. Then we should avoid just overlap, the topic. So we are not planning to have cosmic rays, but we could, of course, have it. So now it's good to have this information to have 2 distinct, topics, not to have too much overlap. So certainly we should avoid cosmic rays. But if you have information about the schools, upcoming schools for next year, please also send us so we could take into account this information in our future planning. So now let's again thank all of you. Today was really good attendance. I think we see more than 50. And so it is a bit not often when it's a pure theoretical talk, so that is implies a lot. And so see you in September or October of this year, in a few months. Thank you very much.
Thanks a lot. Thank you,
Bye.
Felix. So the link is, because Rashmi suggested that the link would be open for half an hour in case somebody wanted to start a conversation, but it's finished, right? Or should I get out or not?
Yes, I think we have still 4 minutes if you want, but yeah, I think we just finish now.
Okay. Thanks a lot, Felix.
Yeah.
See you soon.
Yeah.
Bye, and thanks to
Thanks
all
again,
of you.
Pasquale. Yeah.
Yeah,
Okay.
bye. Bye.
Thank you, Paolo.
Thank-
Okay. Thank you.